Now let's start converting. First of all, we know our equation, which is TF equals 9 over 5 TC plus 32. This equation is important for us to convert from Fahrenheit to Celsius or Celsius to Fahrenheit. So first of all, we know that our the Fahrenheit given to be converted to Kelvin is negative 128.6, and we just plug into our equation, and now it's just simple math. We subtract 32 on both sides, and we'll have negative 160.6 Fahrenheit equals 9 over 5 Celsius. We multiply 5 over 9 on both sides to get rid of 9 over 5. So 5 over 9. And now we'll have negative 89.22 for our Celsius. Now we're not done, as we know the question asked for us to convert from Fahrenheit to Kelvin, not from Fahrenheit to Celsius. So for us to convert from Fahrenheit for Kelvin, we just add negative 89.22 degrees Celsius to 273.15. The reason why is because the freezing point for the Kelvin scale is 273.15, and we know that as we explained earlier, the boiling point, the difference between the boiling point and freezing point for both Kelvin and Celsius is similar. So for us to convert from Celsius to Kelvin, we just add 273. We just add 273.15 to the Celsius we have, to the measured Celsius we have. And question, so our final answer will be those two numbers added up, and we get our answer. Now we're not done, because as we know the question asked was to convert from Fahrenheit to Kelvin, not from Fahrenheit to Celsius. So the answer we got for our Celsius is negative 89.22 as we calculated earlier. And now for us to convert it to Kelvin, we just simply have to add negative 89.22 degrees Celsius to 273.15, and we'll easily get our answer correct. The reason why we have to add 273.15 is because the freezing point and the difference between the freezing point and the boiling point for both Celsius and Kelvin is similar, as we explained earlier. So 273.15 is known to be the freezing point for a Kelvin scale. So for us to convert from Celsius to Kelvin, we just add 273.15, and we'll get our answer in Kelvin. So let's just write the givens. We have two masses, one for the spike, which is 0.500 kg, and the other one, of course, for the sledgehammer, which is 2.50 kg. And of course, the velocity is 65.0 meters per second. So they're asking for is the total internal energy, and to find that we have our equation, which is change in potential energy plus change in kinetic energy plus change in internal energy equals 0. In the question they didn't state anything related to potential energy because we didn't find any heights, any altitudes, so we can exclude potential energy from our equation, and now we just have kinetic energy, and delta Ke and delta internal energy equals 0. So we add the two. So this is the equation for kinetic energy plus delta U equals 0. That's what we're looking for. And as you can see, the question says that it says they only wanted one third of the hammer's kinetic energy. So we multiply it by 1/3 of mv squared plus delta U equals 0. We take it to the other side, just simple math, and we'll have 1/3 of mv squared. We don't have to put the negative signs because for these kinds of problems we don't have to worry about the signs, so we can just ignore the negative sign. So now we just plug in of 2.50, velocity of 65 squared, and we get an answer of 1760.41 joules. 41 joules, and that's the unit we're going to be using for these kinds of problems, which is joules. And that's the total internal energy the question asks for. So they're asking for us to find the specific heat capacity of the liquid. So we know that we have this equation for heat, delta T. So in order for us to find Cp, we just simply switch things around, and we have Q over m delta T. Now we just simply plug in. We know the mass is 0.15 15 gram sample, so if we convert it to kilogram, we'll get 0.015. We multiply it by change in temperature, which is equivalent to 300 minus 80. And the heat, of course, we also know, which is the change in heat, of course, we know, which is 15.8 times 10 to the power of 3 minus 8.37 times 10 to the power of 3. And when we do that, we'll get a result of 2. When we just plug it into the calculator, we'll get a result of 2.25 times 10 to the power of 3 joules per kg degrees Celsius. For the second question, they're asking for the latent heat of fusion. So, latent heat, we have two kinds, fusion and vapor. The equation, just to quickly remind you that latent heat is the amount of heat that's needed to change the state of matter, not the temperature. So we know that the equation for both latent heat fusion and vaporization is equal to L equals Q over M. L equals Q over M. We know our Q, which is 7.1, and we know which can be seen from when we subtract 15.8 and 8.37, and we know that it's fusion because fusion is dealt with when when something is transformed from solid or ice to liquid, and here this is where this is the transformation where it went from solid to and liquid to pure liquid. So 15.8 minus 8.37 gives us 7.1, and we know our mass, which is of course 0.015. We'll get an answer of 4733 joules per kg. Our third question is the specific heat capacity of the solid. Let's go back to our graph. So the specific heat capacity of the solid is 1.27 times 10 to the power 3 over 0.015 times 80 minus 0. And we just plug it into the calculator and we'll get an answer of 1.05 times 10 to the power 3 kg J per kg degrees. For these types of questions, I suggest you draw a table to deal with the two substances in a question. So in this case, we've been asked to deal with silver and water. In this table, identify the mass, the Cp, and the initial temperature of both silver and water. They'll have the same TF, which is the same final temperature. So that's what we're going to work on, finding the final temperature for both the water and the substance. So we've been given that the mass for silver is 25.5 grams. When you divide it by 1000 to get it in kilograms, we'll have 0.0255 kg. Cp, its Cp is also given, which is 234 joules per kg degrees Celsius. And the initial temperature is also given, which is 84 degrees Celsius. The mass of water is also given, which is 5 times 10 to the power negative 2 kg. The Cp of water is known from our table, and it's of course 4186 joules per kg degrees Celsius, and its initial temperature is 24 degrees Celsius. So now we have to, for these kinds of questions, this is what we do. We do Q lost equals Q gained. So for Q lost, it's of course silver, and for Q gained is water, of course. But keep in mind that this question has a little trick in it. If you can go back to the question, it says that the calorimeter is not perfectly insulated, however, and 0.140 kilojoules of energy is transferred to the surroundings before a final temperature is reached. So there is some lost heat going to the surroundings. So this is what we do. We add to the heat gained on water plus 140, because when you if we want to multiply kilojoules to joules, 140 joules. When we want to multiply convert kilojoules to joules, we multiply by 1000, and this is what we did, and we got 140 joules. Anyways, so we put a negative on the heat for silver, and we keep on solving. Plus joules, and the equation is negative CPM delta T equals CPM delta T plus 140 joules. We keep on solving. We just plug in the givens. 234 times 0.00255 TF minus 84 equals 4186 times 5 times 10 to the power negative 2 times TF minus 24, of course, plus 140. And when we do the multiplication, we'll get negative 0. Simple math, 585 TF plus 49.14 equals 209.3 TF minus 50232 plus 140. So simple math, when we do our simple math, we'll get, and we take these to the other side, we'll get 4932.34 equals 209.885 TF. We divide 209.885 on both sides. And our final temperature for both silver and water, because as we said they have both the same final temperature, is 23.5 degrees Celsius.